Okay, so here we have that RL practice assignment that I attached under content in D2L. And so we're going to look at the two tables, the series RL AC circuit and the parallel RL AC circuit. And we're going to start with the first example here. I'll just show the first example from both tables. That'll give you the procedure and how to approach it. And then you can continue on with the rest of it. And I'll also show confirmation of the values in multisim as a demonstration as well. So if we're looking at this, the first thing we're going to do is look at the values given in the first part of the table, and I've labeled them in the schematic above here, and that's 10 ohms for the resistor, and then 100 millihenries for the inductor as a 0.1 Henry value. So then what I'm going to do is use the frequency, which is given as 60 hertz from the source here. So you can see a 60 hertz source. And I'll use my XL equation to determine the value of XL. So I've got 37.7 ohms for XL here. The next thing I did was I created an impedance triangle. So we're starting by determining total opposition here. We have a simple circuit. We have an E total value that is 120 volts. So our next step is to determine total opposition. So I'm demonstrating that by an impedance triangle here. Really, all you need to do is understand you can write that as a rectangular value and convert it to polar, but I'm kind of using all the steps to make it a little bit more visual here. Remember, XL is a plus J component. So I've indicated a plus J component to XL here, and my value of R at 10 ohms at 0 degrees. Now that means that you're going to have a Z total value at an angle of phi or phi here in the impedance triangle. Z total could be written here as 10 ohms plus J 37.7 ohms. Okay, so there's my total impedance as written in rectangular form. Then I can, of course, convert that to its polar form. And in order to do that, I'm going to need my calculator and calculate the value in polar. But let's just start by putting that in here. Okay, so Z total is 10 ohms plus J 37.7 ohms. Okay. Okay. So now I'm going to do the rectangular polar conversion for this impedance, and the polar value then is going to be Z total equals 39 ohms, and I'm just going to toggle to the angle here, and the angle is 75 degrees. Okay, so then down here you'd put in your 10 ohms. Sorry, you'd put in your 39 ohms at 75 degrees. Okay, so that's telling us that our angle phi, or our angle of impedance, is 75 degrees. Now, how can we go about determining that angle of that current with respect to the applied voltage? Well, what we can say is I total is going to equal my E source value at 0 degrees divided by my Z total value at angle phi or phi. So if I put this in at 120 volts at 0 degrees divided by 39 ohms at 75 degrees, I'm going to get a result of 120 divided by 39 is 3.08 amps, and the angle will be one that's the angle equal and opposite to 75 degrees. 0 degrees divided by 75 degrees is going to give us minus 75 degrees. Okay, so what's that telling us? That's telling us that the current is going to be lagging that applied voltage by 75 degrees. So now we've got our total current, and we know that in series our current's going to be the same for all components. So we know that as far as current goes, I total is going to equal IR is going to equal IL in this situation. So because current is our common quantity, we can multiply it by each one of the values of opposition here in order to give us our voltage. So let's do that. Let's actually come up with our value here for VR and VL, even though that's not part of what we've assigned here. VR then will equal 10 ohms times, and what was our current? 3.08 amps. So that's going to give us 30.8 volts. Okay, what about VL then? VL is going to be our XL value times our current. And remember, our XL value was 37.7 ohms times 3.08 amps. Just going to run that through my calculator. 37.7 times 3.08. You come up with 116.1 volt. Okay, so those are both ACR. So just going back here, what I'm going to do is I'm going to demonstrate the Kirchhoff's voltage law using a voltage triangle here. And so what I'm going to do is just above this impedance triangle, I'll show the voltage triangle. Now, when it comes to the voltage triangle, realize that, sorry, I'm doing all my stuff here, but realize that you're really going to have a triangle that looks exactly the same as the impedance triangle, because of course every quantity is multiplied by I total to give you the result. So that is to say that VR is determined by R times I total, right? So I total times R. VL, I total times XL. And ES is going to be Z total times I total, right? So what does that look like? We had our voltages there. So we're going to have 30.8 volts, and we're going to have a plus J value of 116 volts, and that means the hypotenuse here, ES, we know better equal 120 volts. What's this angle going to be in here? Well, it'll be an angle equal to phi or phi as our angle of impedance, which we said was 75 degrees. Now, notice how we said the current lagged that applied voltage. Well, it lagged the applied voltage, and you may say, well, that doesn't look like it's lagging in the voltage triangle. But notice how in the voltage triangle, it's not our applied voltage that's the reference, it's the VR value. So if we were to simply look at the current, which we know is going to be in phase with VR, being right here at I total, notice how we have a relationship that's lagging current from the applied voltage if we use the total voltage as the reference. This is a lagging angle. All right, so that's all supported by our acronym that we know for an inductor circuit is ELI. The current will lag the voltage in an inductive circuit. And no doubt we have an inductive circuit based on an inductive load in series. So sure enough, current's lagging voltage. Now, if you were to go and put your your rectangular value for your voltage here as E source equals 30.8 volts plus J 116 volts. Go ahead and do a rectangular to polar conversion on that. So I'll just do that now. 30.8 with a plus J 116. Then convert that to polar. Then sure enough, you have a 120 volt value at 75 degrees. So we've confirmed that, right? So ES is 120 volts at 75 degrees. Okay, so next thing I'm going to do is go back to multisim, and I'll just show you how using the oscilloscope we can verify that. Okay, so here we go. So if you take a look here, you can see that I've set up that circuit. I've got a 10 ohm resistor in series with a 100 millihenry or a 0.1 Henry inductor. I've got a 120 volt VAC source connected as the source, and it's showing a 0 degree as our reference there for our source voltage. So when I look at this ammeter that I've connected in series, AC ammeter to measure the RMS value of current, you can see that we have 3.077 amps, which we determined was 3.08 in our example. And we then use that to determine our drop voltages both for the resistor and for the inductor. So if we look at the example for the first one, we got 30.8 volts, which is what we were calculating. And then for the second one, we have essentially 116 volts. Now we had our 116.1, but don't forget we used a little bit of a rounded up current, and our value that we used to calculate for our angular velocity was not exactly to the 2 pi f value in a 377 angular velocity, which is just generally used for 60 hertz. But there's certainly no worry in these results. They're confirmed by our calculations and our analysis, so we're happy with that. But first of all, just so you remember, this is something we have to really start to get our head around, and that is, remember when you're working with AC volts and reactance in a circuit, these two voltages are not in phase anymore. So what I mean by that is that the resistor voltage at 0 degrees and the inductor voltage as an imaginary value of plus J, it creates a voltage triangle. And the voltage triangle is what proves Kirchhoff's voltage law here. So you need to understand that, and if you were just to add 30 volts to 115 or 116 volts, you know you get 146 volts, which is certainly not the source voltage. But if you were to show it properly in an voltage triangle, then no doubt the hypotenuse of those two voltages, when you take 30.8 at 0 degrees and add it to 116 at 90 or a plus J, the hypotenuse, you can prove it, check it out, do your rectangular polar conversion on that, you'll get 120 volts, and that way you verified Kirchhoff's voltage law. Okay, so we're back to our multisim circuit here, and notice how I brought in an oscilloscope here, and it's a 2-channel oscilloscope. Notice how one of the channels, channel A, I've got across the resistor, and the other channel A, or channel B, sorry, I have across the source. Now remember, we're looking at the phase angle. We want to know the angle between the current and the applied voltage. That's what we call the circuit phase angle. So through the use of the oscilloscope, I can determine the angular displacement between the two waveforms from the oscilloscope. But what I did want to mention is anytime you have a resistive component within a series connection on an AC circuit, then the voltage across that resistor is going to represent the phase of the current, because we know that the resistor voltage and current are always in phase. You can't rewrite that. They're always in phase. And an inductor will always be 90 degrees out of phase with that, with its voltage. So the voltage of the inductor will be 90 degrees out of phase with its current, but the resistor will be in phase. So that means if I look at the sine wave for the voltage of the resistor, I'll be looking at the phase relationship for the current as well. So in doing that, then I've got the blue waveform here, or the blue sine wave is representing the source, and that's indicated by the blue test lead. And then the red one is the current. Okay, so now that you know that, then red, current, and blue is voltage. Now if I just bring that oscilloscope in so you can see it a little better. Now if we look at the voltage is going positive. Now I'm just going to move cursor number 2 over and line it up with the the zero crossing of the current, and now we've got a time delay. And if we look down here, the time delay is 3.446 milliseconds. You can see it right down here. And so what I can use is I can use that to determine the angle, because we know the period of 60 hertz is 16.67 milliseconds. So I'm going to take 3.446 divided by the period for 60 hertz, 16.67. They're both in milliseconds. Then I'm going to multiply that by 360 degrees as the amount of degrees in one cycle, or 16.67 milliseconds. And I get a result of 74.5 degrees. So that just means my markers aren't exactly where they should be, but I've verified my 75 degree phase angle with the current lagging the voltage. So remember, the lagging angle is a delay. So lagging from the voltage here is the current 75 degrees later, or 3.446 milliseconds later for a 60 hertz signal.